Hello, my name is Derek, and my partner Alex and I created a CNN from scratch using Python and the NumPy library. To start, I will talk about the components we made to build the CNN, and then I will show you how they came together to form our network. After that, Alex will show you how we do feed-forward, backpropagation, training, testing, and prediction. Then finally, he will show you an app we made that utilizes our model. Let's start by talking about the convolutional layer. On initialization, this class takes in 5 parameters: an input shape, like an image or a set of feature maps, number of filters that we will convolve over our image, a kernel size, or the size of our filters, a stride, or how far our filter will move across the image each time it convolves, and padding, a true/false value whether we will add padding to the image or feature map we convolve. All these parameters are used to initialize the layer. One notable part of the init function is that we use glowrot initialization to set the filters. This is done with np.random.normal set to a scale of 2 divided by the number of weights to initialize. Next is the convolve function. This function sets the padding and stride and moves a filter across an image or feature map, and then returns a new feature map. Conv is the function that makes calls to convolve. This function sets up the feature maps array to store feature maps in, and handles 2D or 3D convolutions. It is what allows the convolutional layer to work. The next component we created is the flatten layer. This layer calculates an expected parameter total from a feature maps matrix and then flattens the feature maps into a one-dimensional array, which we can then feed to a fully connected layer. The fully connected layer takes an input and nodes to initialize. The input is an expected total of connections from, say, a flatten layer, and the nodes are the amount of nodes in the fully connected layer. These values are used to initialize the weights and biases, which is done with glowrot. The feedforward function then takes in an input and calculates the dot product of that input and our weights using np.dot, and then adds the bias. Finally, the function returns the softmax activation of the output. In terms of activations we use in our project, we have 2. The leaky ReLU, which returns a value if it is greater than 0 and attenuates it by 0.01 if it's less than 0, and the softmax, which gets the exponentiation of our output and then divides it by its sum. In this way, we can get class probabilities as output. As a multi-class classification error function, we use cross entropy, where the negative sum of the target labels multiplied by the log base 2 of our predictions gives us an error value. Finally, we put all these components together in our CNN class. Here, we initialize C1 as a convolutional layer taking in the input image shape, 8 filters of size 5 by 5, set a stride to 2, and pad the images. Then we feed the output of this layer to C2's input with the same parameters. We then feed the output of C2 to flatten, and then flatten to our fully connected layer of size 10. This will effectively create a CNN that looks like this. And with that, I'll turn the presentation over to Alex to talk about the functions of our network.
So I'm going to show you how to use our CNN and what it does inside. First of all, we're going to need to get the train data and the test data. After that, we're going to initialize our CNN, passing one of the images inside. When we do that, our CNN sets up all the layers using the shape of the image we provided. And we're using 2 convolution layers, one fully connected layer, and we're flattening the input in between. After that, we can train our CNN on the train data, configure a number of epochs, and the limit of images to train on. And inside train, mostly two things happen. We feed forward each image, and then we backpropagate on the correct output. Inside feed forward, we just pass the image through all the layers, using the activation function in between and flattening before the dense layer. Inside backpropagation, we do the same thing but backwards. We pass it through the dense layer, we reshape it, which is the opposite of flattening. We're using the derivative of the activation function, and we're passing it through both convolution layers. We're going to train on a small number of images just to make it faster. After we're done training, we're going to want to evaluate how well our CNN performs. Inside test method, we're mostly doing feed forward on each image. We record the result, either correct or incorrect, and we get the mean result as an accuracy. We're going to test on 10 images just to make it faster. You can see that in this case, the CNN that we trained on 20 images has 10% accuracy on 10 images. We can feed forward just a single image as well. In this case, our CNN thinks that this is number 1. We can save our model to a file so that we don't need to retrain it later. We can also load the model that we trained on 50,000 images. And we can test it on 10 images as well. We can see that the model that we tested on 50,000 images has 80% accuracy. We also made an app that lets you recognize hand-drawn images. For example, now I'm going to draw 2 and recognize 2. I'm going to draw 3 and recognize 3. I'm going to draw 4, recognize 4. I'm going to draw 5, recognize 5. I'm going to draw 6, recognize 6. I'm going to draw 7 and recognize 3. Thank you very much.